Live. Go ahead. Yes, starting on the 16th. That is the beginning of the second marking period and the beginning of this new 5-day-a-week schedule.
What time does school get out?
Oh. Hold on. I thought I knew this off the top of my head, but apparently not. Let me flip back into my email real quick and see if I can't find that new schedule. Phase 2 reopening schedule. Okay, hold on. I'll flip it back. I tried showing this during the live stream, or the, not the live stream, but the virtual Friday before we left. Okay. But this is the proposed schedule that obviously, as long as they don't not cancel school, I shouldn't say, as long as they don't, send everyone home, this is the schedule that we're going to stick to. Now, as a side note, if they do send us into lockdown again, I have no idea what they're going to expect of teachers. I have no idea what they're going to expect of students. If we go into lockdown again, my best understanding is that teachers would, and I'm going to put this in quotes, teachers would be considered essential, meaning we would still be allowed to come in. I would still be in my classroom, but then I would just be virtually teaching to everybody. I think. So if that's the case, then I believe we would still be sticking to this schedule, I think. Again, I have no idea. But school is supposed to start a little bit earlier. I mean, yeah, homeroom's the same deal. Homeroom's the same deal. Arrival's the same deal. But then first period starts a little bit earlier at 7:20 instead of 7:25. And then it's like hour-long classes. 4-minute passing time, hour-long class. 4-minute passing time, hour-long class. Then 4-minute passing time, and then like an hour and 8 minutes. And then there's the dismissal. At 11:40, you all get out. I believe there's like grab-and-go lunches and things of that nature. And then afterwards in the afternoon, that's all for me mainly, almost all for me. All the stuff in gray is me. I have to do all that stuff. Yay, me. But then on Tuesdays, every Tuesday and every Friday, they would have a virtual class meet. Now, what do you notice about, it's really small for those of you in the chat, and for those of you in the class right here, it's really small. But this virtual class meet, it's 10 minutes long. 10 minutes. Oh my, what do we, well, please think of the virtual meets as office hours where students can check in and ask questions. That's what they're really going to be using that time for. So basically on those Tuesdays, Fridays, I'm going to be sitting there waiting for people to even show up. Go ahead.
So that's after school, those things?
Yes, after 11:40, there's a lunch for teachers in the middle, and obviously students have to travel home and whatnot. But then all that after school schedule is mainly for me, but then the Tuesday, Friday one would be optional. Show up if you need extra help or have questions. Yeah. Again, we're going to be relying on Google Classroom a lot more. This is a fun year. It's going to be one of those years where it's like your kids are going to be like, oh, Mom, Dad, you won't believe what they're making us do in school. Well, you did in school, You ever have to walk uphill both ways? It's impossible. Anyway. Near the end of January. Yes. I am not entirely certain. I don't have the full calendar in front of me, but near the end of January, we do midterms. For this class, it would be final exams because it's a half-year class. And then after that week of midterms, you guys would transition into your second semester, in which Prob Stat would be no more, and I would be teaching this class called Discrete Math. Yeah. So I don't know if you'll get a new schedule, like printed schedule, but it'll be a new schedule. Yay! But yeah, next week I should see you Monday, Wednesday, Friday if everything goes as scheduled. In the meantime, I have some information that I want you to write down, and I have a discussion that I want to get going with it. So let me start with the basic discussion real quick. You guys are basically familiar with the concept of track and field. Is that fair to say? Cool. Yes. And if there's somebody who does exceptionally well in an individual event for track and field, you would consider that person to be, they're a pretty good athlete, right? Cool. If I had somebody who did the long jump. What type of athlete? How would you describe the type of athlete who does the long jump? What type of physical attributes do you need to have in order to compete well in the long jump? Maybe. What else? You got to be fast. You know? You got to have strong legs. Absolutely. Yeah. You got to be able to jump. You got to have strong legs. You got to be fast. You got to be quick. You know, the general idea of the long jump is like you run, you get to the spot, and then you propel yourself upward in an arc, and then you land. But then as you're flying through the air, you're like bicycle kicking or something. I don't know. So what type of physical attributes do you have to have in order to do well in the shot put? Yeah, strong. Just for the sake of reference, the shot put, you get the, I don't know how heavy the ball is, but you gotta like, you get the thing together, and then you like do a little spin, and then you boom, you know what I'm saying? Yeah. So you gotta have strong arms. Like what? Like strong arms where exactly? Your whole upper body. Yeah, I would say. Is it fair to say that a long jumper would be a bit leaner, obviously to be, thinner, to be, and then when you see a shot putter, that might be a bit bulkier or something like that? Like a lineman, exactly. Like a lineman, the offensive, defensive, whatever, what have you, cool. So if I had in this room right now a shot putter and a long jumper, would you be able to tell me who was the better athlete? Ooh. Why?
Because they're
Two different things, two different sports, two different sets of physical attributes that you need to have. What if I told you there was a way to compare them? I know, right? Order now. Ladies and gentlemen, what I need from you, I'm going to need those notebooks out and open.
Oh my gosh, now when we go back full time, I'm gonna need actual binders for my actual classes. I shove everything in one box. They really did me like that.
Well, they didn't. No, whatever. Shut up. Oh, goodness. By the way, for the sake of argument, in terms of the election, here's my correct so far. There are still, I think 4 states remaining to be called.
Wait, 279. I thought when I stopped watching it was like 271.
No. Well, again, I'm basing mine on CNN. Different news outlets have different numbers. So, but based on the CNN projections so far, I've gotten 94% of the states correct. I've gotten 96% of the Senate races correct. I've only got 2 wrong in the whole Senate. And then I got 98% of the House correct so far. I don't know. I'm hoping.
So the House is remaining Democratic and the Senate remaining.
Correct. The Senate is staying at a 52 majority, my projection, for the Republicans, because there's 4 races left to go, and the Republicans are ahead in all 4 of them.
So all states are counted, right?
What?
All states haven't counted.
For the presidency?
Well, for the president, I think that's over.
Yes, it is over. It is over, but there are still states left to be counted. But it is over. This is done. This one is clearly not done. You can see the 51 majority. This one's not done, but the 4 remaining races are going to go Republican. This one, you can see, is not done, but it will end up being like 221, 222 Democrat.
That's really close.
Yeah, but it was 235.
Yeah, I lost a lot.
Yes, they did. Anyway, back to this. So, talked about a shot putter, talked about a long jumper. Where is this leading? I'm going to title this thing normal distribution. That's the title that I'm going to give to it. Normal distribution. Today is the 9th. See, the funny thing is, with COVID and all this stuff, I've had to sacrifice a lot of the things that I've wanted to teach and the time that I've had to do it in. Compared to last year, we're roughly only 2 weeks behind, if you think about that. And that makes sense because I'm only seeing you guys once a week.
So technically, if we were here full time, the time would have been made up.
Say again?
If we were here like 5 days a week, we wouldn't be 2 weeks behind because we would make up the time that we missed.
So to speak. So to speak. I'm going at a more deliberate pace. I've had to sacrifice some of the things that I've wanted to teach. Like some of the experiments that I've wanted to do, like going out and actually collecting data and doing. I've had to sacrifice that because we literally can't do that, you know. But anyway, let's talk about two athletes. I want to talk about athlete A versus athlete B. Now, athlete A and athlete B, you do not know what they look like at all. But you do know that they have competed in two different track and field events. They have both competed in the long jump, and they have both competed in the shot put. Now, as we've discussed, these are two completely different events. These are events that require different physical attributes. Now, athlete A in the long jump jumped 6.78 meters. Athlete B jumped 6.30 meters. All right, cool. Clearly, athlete A jumped farther. I guess you could say that athlete A is the better long jumper. Yes, you are totally allowed to say that. Now, yes, it was one jump, but let's just assume that this is typical for these two athletes. In the shot put, athlete A threw that thing, whatever the ball, 14.77 meters. Athlete B threw it 16.40 meters. Clearly, athlete B is the better shot putter. Athlete B threw it a bit farther than what athlete A was capable of. Now, at this point, there are several things that people would point out to me. They would say, well, again, Mr. Markey, look at this. Athlete A only jumped about 0.48 farther, almost like 0.5 meters farther. But athlete B almost threw 2 whole meters more than athlete A. And I would say, yes, absolutely. That is a valid thing that you can say. But you ever hear the phrase comparing apples and oranges? Well, remember what you said before when you said you're comparing two different things? That's the phrase, comparing apples and oranges. You can't straight up compare an apple to an orange. You can't just say, well, which one tastes better? I don't know. It depends on who you are. It depends on what you like. There's different varieties of apples, different varieties of oranges. You can't just compare apples and oranges. You can compare an orange to an orange. You'd be like, okay, this is like one of those tiny little cutie oranges that you can like pull apart and stuff like that. And then here's like a giant like Florida orange that like you try to open it and the whole thing squirts in your face. But they're both oranges and you can compare them. Apples, you can do the same thing with apples. Here's a Granny Smith apple. Here's a Gala apple. You can compare them and say, okay, we could talk about differences, but they're both apples. You can't compare the long jump to the shot put. We need more information. Let me give you more information. More information that you may need is something like this, X bar. X bar is the mean. Now, what I'm going to tell you about X bar is this. Let's say that these two athletes competed in a competition on one day. They both competed in a competition, like a high school competition. Doesn't matter. Just giving you a little context. And in this competition, there were hundreds of kids who participated in the long jump. Hundreds of kids who did the long jump. And on average, the long jump average was 6.16 meters. At this point, you can say, well, clearly, athlete A and B are better than average. They're better than the average athlete at that competition that day. Good for them. Again, which one's the better athlete? Well, they're both good athletes, but which one's better? I don't know. Let's see what happens. Here's the mean for the shot put. The mean for the shot put was 13.29 meters. Once again, they're both good athletes. They're both better than average. Who's the better athlete? I don't know. Just for informally, if you just had to take a guess, because I will eventually reveal to you which one is the better athlete. But if you had to take a guess as to which one you think is the better athlete, again, shot put, we talked about the physical attributes of throwing a shot put. We've talked about the physical attributes of doing the long jump. You can see how much better than average they are. Clearly, they're both better than average. How many people, just again by a show of hands, how many of you guys would say, yeah, athlete A. Athlete A is my guy? Okay. How many people would say athlete B? Okay. All right. Cool. Let's just see what happens. Now, you seem like the lone duck saying athlete A. Why is that? Okay. That's true. Okay. All right. And why would you guys say athlete B?
Well, he's also good at long jump.
Yeah. See, the thing is, it's like when people try to compare sports to each other. Like they try to compare like the physical attributes of like a baseball player to like a football player or something like that. There's a lot of people who would say marching band's not a sport. It's like, yeah, but do you know like the physical like necessity that you have to do marching band or something like that? I know a lot of people look at cheerleading like that and say cheerleading's not a sport. Yeah. But it's like, again, you're comparing apples and oranges. It's like, I'm going to give you one more piece of information here. Down here, I'm going to give you standard deviation. Standard deviation. Now, standard deviation, as a reminder, this is very important. Standard deviation is on average, what is the deviation from the mean? There are a bunch of people who deviate less than the mean. There are a bunch of people who deviate above the mean. But on average, approximately, how much do they deviate? Well, on average, the standard deviation for the long jump is 0.23 meters. Meaning on average, people are either deviating more than or less than 0.23 standard deviations. And for the shot put, the average deviation is roughly 1.24 meters. Now, standard deviation is a huge thing. Standard deviation tells you how spread out your data is. Standard deviation shows you how varied your data is. Meaning for the long jump, there was much more consistency. There's much more consistency in the long jump than there was in the shot put. Meaning if I were to graph all of the results for the long jump, they would be much closer together because of the smaller standard deviation. The shot put, their data points would be a bit more spread out because of the standard deviation. I'm not going to give you any of the other athletes. I'm only focusing on athlete A and athlete B. This is all the information we need. What's longer, 1 kilometer or 1 mile? A kilometer? So like a 5K, 5 kilometers is roughly 3.1 miles, right? Yeah, so a kilometer is longer than a mile. But you have to think about it for a little bit. It's just like, man, I got to convert. See, because the thing is, it's like, we in America, we deal with the English standard system or some junk like that for some reason. I don't know why. It's really weird. We really should be converting to the metric system, but people have refused to convert to the metric system for years. If you've looked at your car's speedometer, have you guys looked at your car's speedometer? Did you know that they have miles per hour on there, but they also have kilometers per mile? Yeah. They did that back in the day because they were just like, yeah, we'll be converting to the metric system soon. And now it's just, they just leave it there. It's just it kind of is. Maybe if you drive to Canada with your car, you'd be like, oh, thank God I have this kilometers per hour thing on here. Yes. And most of them are in French too.
Oh my God.
Yes. Drive to Canada. Anyway, but my point is, you can't measure a distance. Like, I can't measure a distance in miles and you measure it in kilometers, because we're going to get two different numerical values. We both have to be measuring by the same ruler. You can't be working in like how much milk is in a milk carton? In a milk carton? No, yeah. A gallon. But a gallon's not a standard measurement of measuring things. In science class, what do you usually measure liquids in? Liters, not gallons. You ever see, like, it's funny because when you get like a jug of soda, you don't say it's like a gallon of soda. So you think, oh, I got like a 2 liter. Yeah. Why is that? It's like, I have to go get a gallon of milk. Oh, get like a 2 liter of soda. They're two completely different standards of measurement. One's a metric system, one's an English system. I don't get it, but there is a way to measure these two athletes. There is a way. And I'm going to show you that standardized measurement. It is amazing. So hold on a sec. There's my paper. I had extra paper here somewhere. There it is. I was so hyped on election night. You should have been there. You'd have been like, yep, that's him. I'm going to call it a Z-score. Now, you look at that and you're like, seriously, he's off his rocker. What the heck? Z-score? You're just making stuff up at this point. No, I'm not. A Z-score is a standardized, if I could spell standardized measurement for data. It tells you how many standard deviations, and now I'm going to abbreviate standard deviations. It tells you how many SD, standard deviations, away from the mean a point is. And here's the calculation. It tells you how many standard deviations away from the mean a data point is. This is what a Z-score is. The Z-score is going to be very important. Standard deviation. I originally introduced standard deviation weeks ago. Defining standard deviation, trying to get you guys to calculate standard deviation using what the calculator gave you for standard deviation. And now it's coming into fruition, the reason why we need it. You need to know how many standard deviations away from the mean a data point is, and this is the calculation. Using this calculation, we can definitively determine how good of an athlete you are. If you are above average, you are going to have a positive Z-score. If you are below average, you are going to have a negative Z-score. Z-scores could be positive or negative, and depending on what they are, tells you whether or not you were above or below average. Most data points will fall within 2 standard deviations of the mean. Meaning most data points are going to fall between a Z-score of -2 to +2. Let's see where these athletes fell. Oh no, my clip. There it is. Let's talk about athlete A. So, Athlete A, here we go. In the long jump, I'll just put long right there, 6.78 minus 6.16 divided by 0.23. Now, I've already done the math for you, so don't worry about that. But look how that calculation was done. Athlete A's data point was 6.78. The mean, the X bar, was 6.16. And the standard deviation, S, was 0.23. If you did that calculation, then you would get 2.70 for athlete A. Athlete A, on average, performed about 2.7 standard deviations above the mean. That's pretty good, actually. I have to say, honestly, if you are within 2 standard deviations, that's where most people fall. If you're above 2 standard deviations, you're a pretty good athlete. That's really good. Just saying. Let's look at the shot put. Shot 14.77 minus 13.29 divided by 1.24. Again, this is athlete A. I'm only dealing exclusively with athlete A at the moment. Athlete A's shot put was 14.77, good for them. The average was 13.29, and the standard deviation was 1.24. It was above average. Yes, it was definitely above average, but it was about 1.19 standard deviations above the mean. You cannot compare apples and oranges. You can't. You cannot say, well, gallon, liters. No, you have to be on the same measurement. Kilometers, miles. No, you have to be on the same measurement. You can compare them because there's a conversion between the two. But I don't think that there's a conversion for long jump, and shot put. There isn't a conversion until you look at z-scores. Because now, this is the important thing. 2.7 standard deviations above the mean. Now, listen to what I just said. I'm going to say it one more time. Listen to what I said. 2.7 standard deviations above the mean. 1.19 standard deviations above the mean. These two numbers are now the same unit. Those two numbers, 2.7, 1.19, are both standard deviations above the mean. What that means, they are both now being measured on the same ruler. This is a standardized measurement. Back in the day, question, do you know why they call it a foot? Do you know why they call that measurement a foot? Back in the day, kings of Europe, they would measure the foot literally by how long the king's foot was. And every time there was a new king, they would have to redefine what a foot was. Isn't that messed up? It is so weird. Until one day they're like, wouldn't it be better if we standardize this? Yeah, it would be better if we standardize this. So they did. And they figured, okay, this is the measurement for a foot. Boom, we're never changing it again. And they haven't. It's still a foot's a foot, 12 inches, That's the standardized measurement. These are standardized measurements. Z-scores. So what we can do with them is this. We can get a total. Because these are now the same unit, we can say athlete A's total was 3.89. On average, athlete A, or together combined, has a combined z-score of 3.89, a standardized measurement. We can do the same thing for athlete B, and we will right now. Let's talk about athlete B. Oh, athlete B, let's see how good you are. Athlete B, in the long jump, here's your calculation. 6.30 minus 6.16 divided by 0.23. Notice, What is the only number that has changed in this calculation? Yeah, the data point for athlete B. It's the same average. It's the same standard deviation as up there. Same exact ones, same location. It's just changing that individual data point. You do that calculation. Let's see what happens. Long jump athlete B, 0.61. 0.61. Interesting. I'm going to show you something on a normal curve in a little bit, but I'm going to use it basically with this because this is going to be very interesting. This is going to be very interesting comparing it to the 2.7. As I said, anything farther than 2 standard deviations is considered really, really good. Or if it's negative, really, really bad. But 0.61, it's about average. It's about average. Hey, what would your z-score be? What would your z-score be in the long jump if you jumped 6.16? What did you say? Oh, 0. I thought you said 1 the first time. You did say 1 the first time. It would be 0. If you jumped 6.16, you hit average right on the dot, meaning your z-score is 0. You're no better, you're no worse than average. Yeah. Let's look at the shot put. Shot put, 16.40, move that up a little, minus 13.29 divided by 1.24. Again, same average, same standard deviation. The only main difference, the only really main difference is that 16.4. And it ends up being 2.51. Absolutely. 2.51. Better than average. Better than most people. Extremely great athlete in the shot put. Good for you, athlete B. What's your total? Your total is 3.12. Who is the better athlete? Athlete A. Athlete A. See, the thing is, even though athlete B is definitely the superior shot putter, definitely the superior shot putter, you can see that being 2.51 standard deviations above the mean. But in the long jump, athlete A is just as good in the long jump. Approximately just as good in the long jump. It's not the same number, but they're about the same. In the shot put, though, even though athlete A is not as good of a shot putter, athlete A is still better than a lot of people. A lot of people. Whereas athlete B is kind of mediocre. Kind of better than average, but kind of towards the middle of the pack. Boom. Athlete A is better. This actually is definitive proof to show that. Now, the only way you get that definitive proof, is if you have both athletes competing in both events. That's the only way that you actually get that proof. Because in track and field, I think it's pretty obvious. If you're like a shot putter, what else do you do in track and field if you're a shot putter?
It's like those sticks.
The javelin?
Yeah.
Okay, like you throw things.
Yeah.
But then if you're a long jumper, I'm going to assume maybe you do like the sprinting events, maybe you do the high jump, what have you. I don't know. I'm trying to think. They used to have discus. Do you know what discus is? Yeah, it's like literally like a stone frisbee or something like that. I don't know. It's really weird. Okay. Conclusion. Athlete A is better. And it's simply because their total z-score was more. Their total z-score was more than athlete B. Let me flip over here. Let me draw you another picture here. Let's draw another picture here. Now, I drew this last time, but now I'm going to put in different information, slightly different information. I drew this last time, though, and I'm going to ask that you do the same. Draw this nice little normal curve here. That is actually amazing. That's the best normal curve I've ever drawn in my life. I'm just going to flat out say it. I think we're done. No, kidding me. Anyway, let's talk about the middle. The middle is typically reserved for the mean. Now, I'm going to do this for the long jump. This is going to be for the long jump. In the middle is the mean, which in this case is 6.16. 6.16 meters. But I'm not going to write meters for now. I was going to put 6.16. The mean should be approximately right in the middle for something that is normally distributed. Then, a little bit down the ways, you have a standard deviation up. You have one standard deviation up. Now, the thing is, I'm just going to add the standard deviation. Hopefully you can see that right there. I just did 6.16 plus 0.23, and that is 6.39. That is one standard deviation above the mean. Two standard deviations above the mean, I'm going to add another 0.23, is 6.62. And three standard deviations above the mean is 6.85. Last time, when we had our class together, which was like 2 weeks ago, oh my gosh, we drew something like this, except I didn't put in any numbers. I just put like X bar and then X bar plus S and all that other stuff. It's like plus one standard deviation, plus two standard deviations, plus three standard deviations to fill out that normal curve. I can do the same thing in the other direction. I'd have to start 6.16 minus 0.23, and that would give me 5.93. And I put that over here, actually. 5.93. I would again do the same thing over here, minus 0.23. I'd get 5.70. I'd do it one more time, and I'd get 5.47. This is the normal distribution of the long jump. When you had all of those athletes competing on that one day and graphed all of their results, the shape of that histogram ended up looking something like this. They were able to calculate an X bar, they were able to calculate a standard deviation, and they were able to create something like this. Now, tell me, just for the sake of argument, what was athlete A's long jump? What was athlete A's long jump? No, I'm sorry, just the data point, the actual distance. 6.78. Okay, so hold on. Let me put this in red. 6.78 would put athlete A somewhere over here. Now, I'm not putting this into my notes. I'm going to erase this in a moment. Here's athlete A in terms of the long jump. And what was athlete B's long jump? 6.30. So less, probably about right here. There's athlete B. Now you can see, based on the shape of this, look at the shape of this. The height represents the number of data points in that particular range. There are more people, way more people, who got approximately where athlete B got compared to the number of people who got what athlete A got. Basically, the farther you go, there are going to be a lot less people who get that distance. A lot less. Think about Derek. You'll remember Derek, my best friend Derek. If this were the adult male heights, where would I be? If this were adult male heights, I would be about maybe like right here-ish. Derek would be like right here. He'd be all the way over. Somebody said last year an amazing statement. They said to me, Mr. Markey, my goal in life, I want to be 3 standard deviations above everyone else. And I'm like, what? That's amazing. They're like, yeah, 3 standard deviations above everyone else. Not in terms of height or anything like that, but in terms of just ability in something. If you are 3 standard deviations above average at anything, you better believe it's amazing. It's amazing. I'm not even kidding. It is absolutely amazing if you are 3 standard deviations better than everyone else. Now, by the way, it does depend. Like sometimes having a negative standard deviation is a good thing. Sometimes. Think about a race. You want your time to be smaller than everyone else's in a race if you're sprinting. So you want like so it really depends on the context. Get rid of the 2 of them. Let's add in some information. Now let's see here. 68% of data points fall within that range right there. 68%. I know I've already given this to you before, but I need to drive this into your heads. 68% of data points fall in that range right there, between -1 and +1 standard deviations. (95%) 95% fall within 2 standard deviations. I want you to think about this for a second. Think about this logically for a second. If you're within this range, you are within the middle 95% of the population. The middle 95%. What percent am I not counting? What percent have I excluded? If I'm in this range and I am between -2 and +2 standard deviations, and I'm in the middle 95%, what percent of the population am I not in? 68? No, technically I'm in that. Technically I am in that because the 68 is included within this. It's really weird to think of it like that, I know. But I could be like right here. Check this out. Athlete B. Athlete B was right here. Athlete B is within the middle 95%. He is. He's also within the middle 68%. He is. Not the top 5%, actually. The outer 5%. See, and again, I'm gonna draw this on the board. I'm gonna draw this on the board. So watch this. Look what I'm filling in right here. It's not the top 5%, it's the outer 5%. Technically, the outliers are the good people. Yeah, the really good people. What percentage is this, by the way, that I just filled in there? Well, this and this are the outer 5. So what's that by itself? 2.5. Remember, the outer 5%, if the 2 red shaded areas are 5%, that means that this is 2.5% and this is 2.5%. But we'll get into those details. We will get into those details. Yeah, it's really weird. It's like if I wanted to be right here. Actually, let's just say right here. Let's say right here. There's me in terms of height and jumping ability. Okay, I think that's fairly accurate. Whatever. I'm definitely within the middle 95%, but I'm not within the middle 68%. Just something to keep in mind. Just because I'm outside of that range. That's weird. Back to here. Finally, 3 standard deviations. If you are, I'm going to have to draw this underneath, and typically you'll see a lot of people do this. Within 3 standard deviations of the mean, that's 99.7%. 99.7% of all data points lie within 3 standard deviations. I gave this a name last time, and I want to write it down again just to kind of drive that point home. But this 68, 95, 99.7 rule is known as the empirical rule. It's known as the empirical rule. It's just a fancy name. It doesn't really have any ramifications. It's just that if you hear the empirical rule, this is what they're referring to. Just one of those weird things. I'll have to actually figure out what my z-score is compared to Derek's. We'll do that after I finish a couple of notes. But I definitely want to do like a little investigation for adult male height. Just I think it would be funny. I think it'd be really funny. Anyway. So, a couple of points that I want to make. A couple of data points that I really just need you to recognize. If a data point is more than 2 SD, standard deviation, away from the mean. Now, this could be above, this could be below, it doesn't matter. It is considered, quote, unusual, end quote. You used the phrase outlier before. This is a common misconception. Unfortunately, I can't refer to anything more than 2 standard deviations away as an outlier. I'm just going to write this over here real quick for the sake of argument. If I'm using the word outlier, technically, I am referring to this definition. Anything outside that range is considered an outlier. Yeah, let me move the camera over so that people can see it in the chat real quick. Just so you know, if I'm considering something to be an outlier, it has to be outside of that range. We wrote that definition down weeks ago, you know. And then, yes, absolutely, we found out that Derek was an outlier. Yes, absolutely. But even though Derek is more than, I don't even know, 3 standard deviations away from the mean, he would be considered unusual by this normal distribution because the standard deviation definition here and the quartile definition over there are 2 separate definitions, completely separate. That's why I'm using the word unusual up here. They call it unusually high or unusually low. A z-score is the number of standard deviations away from the mean. You need to remember that a little formula. You really need to remember that formula being z equals x minus x bar over s. We do need to remember that formula. I wrote it down earlier. I'm writing it down again. That is one of those standard formulas in statistics that we do need to remember. And last piece of note information before we do this investigation that I want to get to. If you speak of z-scores, then your distribution is normal. I don't want to give anyone PTSD right now, but geometry.
No, don't get me started.
I know. I did not teach geometry to any of you, but I got to ask a question. What is it called in geometry where when you have an if-then statement, you could read it forwards and backwards and it's like the same, and it's like it's still true? You know what I'm saying?
I know what you're talking about, but I don't remember what it actually is.
Yeah. Like for example, if you have a square, then you have a rectangle, you can't go backwards. You can't say if you have a rectangle, then you have a square. That doesn't work. But in this case, it does work. If you speak of z-scores, then your distribution is normal. I could reverse it. If your distribution is normal, then you can speak in z-scores. I don't know what it's called in geometry. Yeah. The only thing I remember from geometry was like converse or contrapositive.
I remember the Krakatoa.
SOHCAHTOA?
Yes,
Krakatoa was a volcano.
Yes, right.
Yeah.
That's how I remember it. So that's probably why that came out. But
Okay,
that's the only thing I remember.
I got you. Yeah.
And then coloring something. I don't know.
Okay.
I didn't miss Cody, so we did some weird things.
Let me just show you this real quick. Now, you don't have to pull this out right now. I'm not going to ask you to pull this out right now, but we will do this in future class periods. We will do this in future class periods, but check this out. There is something in your calculator on this screen right here. Now, how did I get to that screen? We'll talk about that another time. But this one right here, you see that normal CDF? That normal CDF is the normal cumulative density function. That's what it is. Now, on your calculators, it would say something slightly different, I believe. Let me see what it says on my calculator here. Because I have my phone calculator, and usually my phone calculator has similar, it has similar things that you do. On your calculators, it may look like this. It may look like this. See, lower, upper, mu, and sigma. Mu is your population mean. Sigma is your population standard deviation. It's the same calculation. I just want you to be aware of that. Now check this out. If I type in -1 to 1, what's really interesting is the fact that it gives you this number. What percentage is that approximately? It's about 68%. Now again, I go back to the empirical rule, 68. What's the next one? 95. Check this out. Approximately 95%. See, the thing is, on the graphing calculator, you can actually determine very specific numbers, which we're going to get into in the future. I'm not teaching you how to do this just yet. I just wanted to visually show you what this thing does. And then, of course, the last one, 99.7%. And you can see it's sitting right there. See, this calculation can be done directly in your graphing calculator. You just have to know how to use it. For example, if I bring this back, to Wabadima, there we go. Lower, upper, I have to type in -1 to 1. I'd keep the mu and sigma the same. We'll talk about that again in the future. But if I pasted that, it would give you that 68% again. You can see that right there. So, oh, happy day. All right. Let me Google something real quick here. Average adult male height. Here we go. Okay, hold on. According to the CDC, the average height for American men is 69.1 inches. That's about 5'9". Okay, hold on. Look. Now, you don't have to write this down. I just want to figure out for Derek and me, how do Derek and I compare on the normal distribution? So, average American height is approximately 69.1 inches, okay? Now, in order for me to do this properly, I'm also going to need a standard deviation. Now, I can estimate a standard deviation, but instead, I'm just going to try and see what happens here. Standard deviation. I can spell it. Adult male heights on average are 70. Oh, that's different, with a standard deviation of 4. All right, let's go with that. That's usablestats.com. That's weird. Oh, US Able Stats. What does it really say? Usable. Oh, my word. What is wrong with me today? Stayed up too late on election night. Although that was a lot of fun. All right, fine. So I'm going to use their numbers. 70 inches with a standard deviation of 4. Cool. So let's see where Derek and I rank. There's my little thing. Where is it? Where are you? There you are. There we go. On election night, you should have seen my command center. I had the desktop computer, right? And then I had the laptop to my side where I was updating all my stuff, but I was streaming from the desktop because it was so much easier. And then I had a chair set up with the camera attached on the edge of the chair, facing out at my dry erase board of the United States. And on the actual live stream, you had like the camera on the map of the United States. You had a window of me opening up and updating things on the CNN website using the projection, stuff like that. And then at the bottom, you had my percentage correct. No, I tried to stay consistent because the thing, it's different websites use different projection materials. Like if you know, for the longest time, people were criticizing the Associated Press and Fox News. The Associated Press and Fox News called Arizona for Biden much earlier than everyone else did. They called it on election night, whereas like everyone else didn't call it for like a week or something like that. I'm like, okay, cool. But Arizona did go for Biden. It's just that they called it way too early. They called it, I'm not going to get into the details of it because they called it for at a precise percentage. Right now, Arizona actually hasn't been called yet. Hold on. By most outlets, I don't think that Arizona still hasn't been called yet. Because the thing is, when they called it for Biden, Biden was up by like 100,000, 200,000 votes in Arizona. And right now, Arizona is down to just a 19,000 vote difference. So, with 2% of the vote remaining. But whatever. As I said at the beginning of the class period, the election's over. Okay. It's just at this time, there's nitpicking details. That's not for me to say. That's not for me to say. It is an interesting thought experiment. It is definitely, and I guarantee you there are going to be books written about that. You know what I'm saying? There are going to be books written about this election. They're going to be teaching about this election 50, 100 years from now in school. I guarantee you, you're living through history right now. Like they talk about it. They're like, when I was growing up in the 90s and stuff like that, they were like, oh, you're living in history right now. Like nothing interesting is happening. And then what happens my senior year, 9/11? I know. But anyway, back to this. Let's talk about Derek. So average is at 70. Standard deviation, I'm going to go up 3 standard deviations, puts me at 82. This goes down to 66, 62, and then 58. Now, these are all measured in inches. This is according to the usablestats.com thing, usablestats.com, where inches of adult male heights. Now, again, this is adult male, okay? Obviously, it's a bit more difficult to compare adult male to adult female because on average, adult males are taller. There's nothing we can really do about that. So let's see, where am I? I'm 5'7", maybe. So that put me at 67. Oh, sweet. I'm about right here. There's me. Good for me. I don't know. Cool. Where's Derek? Derek is 6'8". How many inches was that again? Was it 80? I can't think right now. 6 times 12. It is 80. 72 plus 8. There you go. Oh, snap. Derek isn't all the way out there. Now, Derek is definitely considered unusual. He's definitely considered unusual. But, wow, that is really crazy. Look at Derek. Now, for Derek, it would be 80 minus 70 divided by 4, which would give you Derek's z-score. 10 divided by 4 is, I want to say, 2 point something. 10 divided by 4. 2.5? Yeah, 2.5. That's Derek's z-score. Here's me. 67 minus 70 divided by 4, which would be negative 0.75. That's really funny. I don't know. It's just really funny. The difference between me and Derek is over 3 z-scores. That's the difference between him and me. That is nuts. But again, me having a negative z-score just simply indicates that I am below average. I'm below average. But because I'm not even -1, I'm in the middle 68% of all data. 68%. The majority of people fall within -1 to +1 standard deviations. That's crazy. Of course, Derek, unusually high. Now, again, going back to that definition that we talked about, this proves that Derek is unusually tall. The other calculation that we did 2 weeks ago, that proved that Derek was an outlier. 2 separate definitions. I want to be very clear with that. Oh, that is awesome. Now, to wrap up, let me go back to that picture that I had on my phone. Let me go back to that picture that I had on my phone because it was a little sideways, but that is okay. We can still deal with that. Chapow. Chapow. Here we go. Now, zooming out. Now again, this is voter turnout by election year based on proportions, but you can see right here, look at this. 1 standard deviation, that's the middle 68%. Most data points will fall within that range. They'll fall within 1 standard deviation above and below the mean. This is voter turnout. I don't know if I mentioned this to you last time, but like the voter turnout in recent years have been like horrendous. But then in 2016 and 2020, that completely blew it out of the water. Again, 2020 is an anomaly year. It's an anomaly year because if you look at it here, this was over 3 standard deviations away from the mean, or more than 2, I should say. More than 2. It is unusually high. Very unusually high. But everything else kind of just falls right in the middle. Oh, that's nuts. I love this kind of stuff. This is what me and other math teachers do on election night. We literally send each other charts like this. You know. Do you know when it's appropriate to argue about politics? Never. Just saying. Come on. Seriously. Anyway, that's enough for me. Oh gosh, I'm gonna be putting out a review video, not a review, a recap video on the election, to just talk about how I was right about the polls. I was totally right about the polls and how the polls are definitely skewed in one direction, not because people are evil, not because people are doing it on purpose. They're not. They're not. The polls are not being collected appropriately in the sense that they're calling people. They're calling people. I love it so much. Anyway, that's it for me. Next week, let me think what's going on next week. Next week, we come back all together. We're going to high five each other. It's going to be great. Oh, that was the one thing I did. Oh, that was a loud snap. That was the one thing I wanted to say. Last Friday, I did have an assessment due on quizzes that some people did not do. And I'm saying this for everybody. I'm saying this for the people in the chat as well. Hi, people in the chat. Now, for those of you who did it, yay, happy day. For those of you who didn't do it, I'm going to have a way to figure that out. Whether I create another code and then count it as like a late assignment or something along those lines. Counting it as a late assignment would cost points and things of that nature. We'll talk about that when the time is appropriate. But this is the last week of the first marking period. Grades are due by the end of the week, so I got to get this stuff in. If you owe me anything, make sure you are emailing me. I'm trying to catch up on all my emails. Guess how many emails I had when I came in this morning? Like 95 emails. Okay? I've only gotten through about 40 of them. Okay? I got a long day ahead of me. So if you've emailed me over break, please be patient. I will get back to you. But anyway, I'm going to wrap this up because Bell's going to ring in about a minute, and then we're all going to high-five each other from a social distance, whatever. Okay. Goodbye, everyone.